The previous generation of glaciologists were my mentors and my heroes. They acknowledged they did not exactly know where the glaciers were. And when they would go to the Antarctic, they would measure everything they could to try to unravel this mystery. And with remote sensing, we could look at all of them. So everything we looked at led to discoveries because we were the first one to look at that.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring stories of resilience, hope, and scientific insight into climate change. You may have already guessed the focus of today's episode. That's right, we're taking a look at the glaciers of Antarctica and Greenland, and getting a much better understanding of how these two glaciers play a role in our planet's climate. This episode of Down to Earth is brought to you by the Remote Sensing Environment Analysis and Climate Technologies, or REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society. The REACT Technical Committee is a collaborative and supportive venue for all scientists and engineers looking to exchange ideas and share knowledge that advances our efforts to tackle climate change. To learn more and be part of this incredible cutting-edge committee, visit grss-IEEE.org and select the REACT Technical Committee.
There are many times in my work where I thought, I'm so lucky to do this. And I can't believe there's just few people worldwide looking at the same thing. How come they don't do it too? It's so amazing.
This is Dr. Eric Rignot, Professor of Earth System Science at the University of California, Irvine, and Senior Research Scientist at NASA's Jet Propulsion Laboratory. He's a glaciologist whose work focuses on understanding the interactions of ice, climate, and ice-ocean interactions, especially with respect to their impact on the ice sheets of Greenland and Antarctica. He's been studying and working in this field since the 80s, and as a result, he's seen a lot of exciting changes.
When we got access to these radar images from the ERS satellite, the Earth Remote Sensing Satellite launched by ESA in 91, it was the first time we could look at Antarctica and Greenland and look at the motion of the ice with interferometry. So it was a time of exploration. Every new data set we were getting on any glacier in Greenland and Antarctica was the first map of ice motion, the first time we could see the grounding line, which is the transition boundary between grounded ice and floating ice. So all of that was super exciting.
As far back as 2014, Eric has been telling the world that some of our glaciers have passed the point of no return, meaning that they can no longer be saved. That may seem like a very depressing reality to face, but amazingly, this knowledgeable and passionate scientist continues to advocate for hope. Let's find out exactly what's happening and why Eric still feels positive about our planet's future. So for today's episode, Eric, I want to focus on glaciers. When I started doing research for this episode, I discovered how little I actually knew about glaciers. So we talk about them all the time when we talk about climate change, but I think most people don't know much beyond the fact that they are melting. So perhaps we can start with a brief description of what glaciers are and how they are formed.
Yeah, so I think we're all familiar with glaciers in our mountain landscapes, right? If you're taking a hike on the glacier, you know what we're talking about. People are less familiar with the glaciers in Antarctica and Greenland. It's important to understand that even though Greenland and Antarctica are big entities of ice, we call them ice sheets, they are continent scale, all of the ice accumulating in these areas is slowly draining to sea through these rivers of ice, which are glaciers, pretty much analog to the glaciers we're familiar with in our mountainous regions where they still exist. Except these glaciers are very big and they travel much longer distances. So a typical glacier in the Alps is going to be a few kilometers wide. A typical glacier in the Antarctic is going to be 100 kilometers wide. When you stand on it, you don't even have an idea that you're standing on the glacier because it's so big. But these glaciers, these rivers of ice, play a very important role on draining mass from the interior of the ice sheets to the periphery, to the ocean. They are really the vehicle of transport of the ice from the interior to the ocean. They are the controls. They are the floodgates on sea level rise. So that's why it might be confusing. Are we talking about an ice sheet or about glaciers? They're part of the same system. The glaciers are just changing rapidly. An ice sheet might evolve more on timescales of thousands of years.
Just to give our audience a bigger picture, how much of the Earth is covered in glaciers? How does their existence impact the Earth?
Well, the Earth is not covered by a lot of glaciers right now, right? So we have the chance, if I would say, to still have two large ice sheets on Earth today. There were many more in the last interglacial. So we have an ice sheet in Greenland, which is not considered a continent, it's considered an island. And we have an ice sheet in Antarctica that's 7 times bigger than Greenland, which is a whole continent standing alone at South Pole, creating its own climate. So Antarctica is kind of the big one in the southern hemisphere and for the whole planet. And Greenland is kind of a secondary one, important because it's in the northern hemisphere, close to where we are. So that's pretty much 99% of the ice on Earth. The rest that you were familiar with, the mountain glaciers in the Alps, in Canada, in Alaska, in Iceland, Svalbard, and other places, is large on the human scale, but in terms of the total volume of ice on Earth, it's tiny, it's small.
You've already touched on this a bit, but what is the difference between the Greenland ice sheet and the Antarctic ice sheet beyond the size of the glaciers?
Yeah, that's an important point. So Greenland is sort of in a warmer part of the climate. Greenland doesn't stand at North Pole. The tip of Greenland is about the same latitude as Alaska, and the northern part is at 81 degree north or so. Beyond that, the Arctic Ocean is just an ocean. There's no land at North Pole. Antarctica sits on South Pole, and there's wind circulating, ocean waters circulating all around Antarctica. Since the Drake Passage opened up between Antarctica and South America, there's a continuous circulation around the Antarctic. There's no such thing around Greenland. Greenland is part of this set of land in the northern hemisphere. You have Canada, you have Siberia, you have Greenland. It's part of this land that surrounds the Arctic Ocean and makes it actually difficult for the Arctic Ocean to communicate with the rest of the world because it's surrounded by the land.
How are glaciers different from sea ice?
Well, that's a fundamental difference, absolutely. The sea ice is frozen seawater. So it's just ocean water that freezes on and then eventually melts again. So it does not displace sea level. It's the same mass. Sea ice can grow up to 1 meter thick within a winter. If it survives the winter, it can grow up to several meters. 5-6 meters is a maximum thickness for the sea ice. Glacier ice is orders of magnitude thicker. It's not ocean water that freezes on. It's snow that densified slowly into ice and started to deform under its own weight and flow downhill to the ocean. So glaciers can range from a few hundred meters thick to 2 to 3 kilometers thick. So extremely thick. If you drill a hole on top of Bird Glacier and travel down to the bottom, walking, it's going to take you a long time to get to the bottom.
So how do we use remote sensing to study glaciers? Can you give us a bit of history? I know the technology has definitely changed.
Yeah, so the early days of remote sensing, we go back to the spy satellites of the 60s or Landsat, which started in the early 70s. And these satellites were mostly taking pictures of the Earth, pretty pictures as we call it. You could not get what we call geophysical information from them very easily. In order to get geophysical information, you have to have some sort of a calibration of the data. You have to relate the measured brightness of your surface to some physical variable. But initially, having pictures from space of the Earth was just mind-boggling on its own right. The spy satellite pictures of Antarctica in the 60s are the sort of first comprehensive record of what Antarctica looked like. There were some airborne operations by the military before that in the 40s, but the spy satellites, they imaged all of Antarctica. So this was the early days, and then Landsat started that trend because people could actually use this multi-frequency, multispectral Landsat image to say something about the composition of the ground. And that trend kept growing with the instruments becoming better. So today, we rarely use images for pretty pictures. We use images, they're like data arrays to give information on what's on the ground. So what I use myself in our research is radar interferometry. So of course, the instrument is making radar images of the Earth, but it uses coherent illumination. And with that, we can come back over time and measure the displacement of the surface very precisely within millimeters. And that's the information that we retrieve from this data.
A quick note to explain coherent illumination in the context of radar interferometry. So, radar sensors send out microwave signals towards the Earth and record how they backscatter depending on the relative surface roughness. These signals are sent repeatedly, and when there is even the tiniest change in a surface, we're talking millimeter scale changes here, the signals will act similar to ripples in water and interfere with each other. When these signals intersect, the illumination of the signal is stronger, causing it to appear brighter. This is coherent illumination and is what allows Eric to detect when glaciers are moving over time. Now, back to the interview.
To bring that into context, even when I studied my career in glaciology, people would spend months in the field to measure a few points on a glacier. That was difficult and challenging work. You had to come back for several years to do that. And with these satellites, we can get these same fields of motions in just a few days over millions and millions of points, over the whole Antarctic, as a matter of fact. So it completely changed. And now the progression is to ingest an exponentially growing set of data sets. So there's still a revolution in making. There's this first revolution, we have space data. The second one, we can extract geophysical information from them. And now we have a sensor web. We have an explosion in the availability of this data, and we have to learn how to use them.
So in remote sensing, we also look at ground truth. So how do you do this? I mean, it seems really hard to go back and forth, say, Antarctica and check and then you told us like a million points and everything. It seems really hard to actually study glaciers. So how do you do this?
Yeah, that's a good point. So I did a lot of ground truthing myself, and the challenges of doing ground truthing with remote sensing. You're going to go in the field with your remote sensing data in hand and spend a lot of time trying to recognize what these features are in your imagery and what they look like in reality. And it's always a little bit of a discovery and revelation, especially when you use things like radar imagery. It's not intuitive to the human brain to see what the landscape is going to look like with radar imagery. So you're up for some big surprise when you go in the field and go like, oh, this is what this bright pattern looks like in reality. Now I understand it. So for some of these things, for instance, of radar interferometry, to compare that with a GPS station that measures speed continuously, and you compare that with your remote sensing data, you can have a few points, and you're going to sort of evaluate how well your remote sensing analysis is working. We have also the chance of, when we look at Antarctica and Greenland, to include in our scenes places that don't move, emergent rocks and other places that are a natural set of verification for us on the amount of noise, how well we calibrate the data, and so on and so forth. So in the case of ice motion, going in the field for ground truthing and putting a GPS is not now something that's fundamental to do. We have enough expertise in this technology. We know the errors enough that we don't need to do that. That's another point to remember, is that in remote sensing, there are maybe sometimes you can measure a physical variable directly, like ice motion is a motion of the ground. This is something we measure directly. And there are cases where in remote sensing, you infer a variable through some empirical relationship or modeling. It's not something you measure directly. You infer it from the data. And that part is a bit more tricky. And in that case, having ground truth is still something important to have.
Seems really complicated to study glaciers, huh? So Eric, what's the most surprising discovery you've made?
I think that the biggest discovery in the last few years is the seawater intrusion beneath the grounded ice that we did not suspect before.
What do you mean by seawater intruding under the ice? Like, what does this mean?
Well, that means that, when a glacier ends in the ocean, it becomes a float. There's a transition boundary where the glacier is slowly adjusting to flotation. It doesn't float right away. It's very thick, very rigid. So it's bending through the water before it adjusts to flotation. You can calculate how much seawater will move beneath the glacier with the tide based on flotation, based on Archimedes. So you can figure out the seawater is going to move about a few hundred meters beneath the glacier when it's at high tide, and it's going to move away at low tide. And what we found in the last 3-4 years is that these intrusions are going instead kilometers. And that's a major discovery, because it means that the ocean heat can go beneath the glacier much farther than we thought. So if the ocean gets warmer, it's going to impact the glacier in a much more significant way than what we thought.
After the break, Eric explains exactly what has been missing from our calculations of glacier melt and how scientists incorporating this new data are revealing some alarming truths. But fear not, Eric also shares why, in his view, there's still hope. So stay tuned.
Are you passionate about protecting our planet and tackling the challenges posed by climate change? Do you want to be a part of a remote sensing community that brings together the brightest minds in environmental science and engineering? Then you need to check out the Remote Sensing Environment Analysis and Climate Technologies Technical Committee, or REACT-TC for short. Here on the REACT Technical Committee, we believe strongly that interdisciplinary collaboration is key to making a real difference in our world. That's why we bring together experts from various fields to exchange ideas, share knowledge, and advance the science that drives our understanding of the planet. Whether you're a scientist, engineer, or simply someone who cares deeply about the environment, the REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society is a place for you. Together, we can make a difference, one discovery at a time. Visit grss-ieee.org and select the REACT Technical Committee to learn more.
Welcome back. Today we're speaking with Dr. Eric Rignot, Professor of Earth Systems Science at the University of California, Irvine, and Senior Research Scientist at NASA's Jet Propulsion Laboratory. Before the break, Eric revealed a surprising discovery that he and his fellow glaciologists learned a little under 7 years ago, that the ocean is melting Earth's major glaciers much faster than originally thought. How did we miss this major piece to the glacier melt puzzle? And what does it mean for humanity in the face of climate change? Let's dive back in to find out. I feel like we need to clearly define glacier melt for our conversation today.
Yeah.
You've mentioned in the past that there are misunderstandings with respect to how glaciers melt.
Yeah.
Can you explain the difference between what the general public thinks about glacier melt and what is actually happening?
Yeah, so that's a very, very good question. So the traditional view on glacier melt is that they melt from the surface, from warmer air temperature, more solar radiation. You melt the snow, then you melt the ice becomes water. You go from a very highly reflective medium, high albedo, to a very low reflectivity medium, low albedo, that absorbs a lot more heat. It's kind of a runaway phenomena. As you melt the glaciers more and there's less snow, it melts faster. And then the traditional view was that all this meltwater will eventually make its way down to the bed of the glacier and lubricate the bed, make the water pressure at the base of the glacier, because the base of the glacier is usually wet, make the water pressure go higher. The ice can lift up and start to slide faster. And in Patagonia, if I go to Patagonia, that's the first thing I'm thinking about, because there's a lot of rain and meltwater in Patagonia, and the glaciers are going very, very fast. So it's got to be related. In the Antarctic, there's no surface melt. It's cold. It melts a little bit in the Antarctic Peninsula, the part of Antarctica that sticks towards South America. You have a little bit of surface melt, but that melt just percolates down the snow and refreezes in place. It doesn't make runoff. What we call runoff is supraglacial water that flows on top of the glacier and then makes a river that comes on the side of the glacier. And Greenland is a mix of the two. It's an intermediate between Antarctica and Patagonia. There's a lot of surface melt, and all these glaciers are also interacting with the ocean. What we did not know or realize, or for a variety of reasons in the early 90s, is how important the ocean is to these glaciers.
What were we missing in the 90s, and why didn't we see it? What have we learned since then about the ocean's interaction with these glaciers?
Well, in the ocean, everything happens hundreds of meters below the surface. And for a long time, we had very few records of ocean temperature in front of the glaciers. It's a big question mark. There was also a traditional view from the glaciologists that when glaciers end in the ocean, they freeze on. There's actually accretion of ice at the bottom of the ice more than melting. So as we try to unravel what was happening, especially to the Greenland glaciers, but also to the Antarctic glacier, we realize it's the ocean. If you look at the ocean and the rates of melt of the ice in the ocean, which are orders of magnitude larger than at the surface, then just a little warming, a little bit more warm water in front of these glaciers can explain what we've been seeing. To put this in context, you can have a surface melt of about 1 meter per year on a typical glacier, and the melt from the ocean at the bottom is going to be 100 meters per year. So 2 orders of magnitude larger. These glaciers melt from the bottom. And to see that, we need to dip down instruments below the surface to measure that ocean heat down below. It's not at the surface. You won't see it at the surface. That's why we can't see it with satellites. I need to dip down a probe 400, 700 meters below the surface to say, I see the heat. And it's melting the feet of my glaciers. And now I understand what's going on.
This conversation seems really, really interesting for me because, they always say to see is to believe. I come from a tropical country, and sometimes I just don't feel the effect of this whole Antarctic glacier melts and everything else. So on your point, we still have folks in society speculating that current climate patterns are normal. How do we know that the glacier melt we're seeing now isn't normal?
Well, we know it from the pace of change of the glaciers, how fast they retreat, how fast they thin. We know that it's impossible for them to have done that for a long time because we know where they were in the past. But it was impossible for them to retreat and thin and melt at this rate for so long. If you look at the IPCC report and the modeling effort, they show very clearly that the Earth system started to deviate from the natural variability around the 80s. After the 80s, it's very difficult for climate model to replicate the climate system unless they add the greenhouse gas emissions from humans, in which case they can replicate the record completely. But we caught it at the right time, and in Antarctic as well, we caught the system as it was ramping up. And we know it was ramping up because we have been able to go back with satellite data all the way to the early 70s to see how the trend suddenly changed in the 80s and 90s. We have this record now. So we know that back in the 80s, Greenland was not too far from equilibrium. Antarctica was already losing mass, but not too far from equilibrium as well.
So the discovery of the ocean melt of glaciers is significant. And the fact that we've caught this sudden change in the 80s and 90s is also significant.
Yeah.
So what does this finding mean for humanity?
Well, what this means, two things. First of all, is that the study of glaciers is highly interdisciplinary. You cannot solve these problems by just sending a bunch of glaciologists on the field. You need to have interdisciplinary science regrouping glaciologists, physical oceanographer, people running atmospheric models. It's a system, and glaciers are only part of the system. If you want to understand them, you have to understand the climate forcing. That includes the ocean. The ocean was a little bit left out. Now we know we cannot ignore this. In fact, if we don't have good measurements of water temperature around the Antarctic and the depth of the seafloor, I can state with certainty we will not be able to model these glaciers. There's no hope. If you don't have this information, you just cannot figure out what they're doing now and what they will do in the future. It's impossible. So it's fundamental to document ocean conditions around the periphery of the ice sheets and the bathymetry, the depth of the seafloor, fundamental to our research. Until we have that, and we don't have that everywhere, we're stuck. The second thing is the changes in the ice sheets have occurred much faster than we thought. And the fundamental reason for that is that it's not that the ocean got warmer because of our greenhouse gas emission. Suddenly the ocean is warming up because we absorb more heat. There's some of that, but the more fundamental reason why the water started to attack the glaciers is that the winds changed. So the winds drive the circulation of ocean heat. And both in Greenland and Antarctica, the changes in wind, changes in atmospheric circulation caused by the change in our climate started to push more warm water towards the glacier. It's not that the warm water was not there before. It was there, but it got pushed towards the glacier faster. So that's kind of a climate trigger that was not in the models in the 80s and 90s. It was not there. So the ocean is an enormous vehicle of changes for these glaciers. It contains enormous energy. If you warm it a little bit, the glaciers feel it. It melts them like crazy.
And I know this is a bit of an obvious question, but what kinds of impacts are we looking at with glacier melt, both in terms of impacts on human settlements and impacts on our climate?
Well, so the first and most important impact is sea level rise, of course. Everybody knows that the glaciers are melting. You displace mass from the land into the ocean. You raise sea level. There's enough ice in Greenland to raise sea level by 7 meters. There's enough in Antarctica to raise by 60 meters. So sea level rise, right? And sea level rise, once sea level rose and you have too much water in your backyard, you can't scoop it out. It's there to stay forever, right? Reversing the system. Well, we don't know how to do that. Well, we're going to freeze the ocean and stack it up. Well, good luck. So it's an experiment we get to do only once. And it's creeping very slowly. Sea level used to rise 2 millimeters per year, and now it's almost 4 millimeters per year. That seems like nothing to the average person, but we know, the scientists know, that this is just the beginning of a curve that goes faster and faster. And we're already on a pace to have a meter sea level rise for the 21st century. And if the trend were to continue in terms of our climate warming, we would go into multiple meters of sea level. But we don't have to go there to even be in trouble. 1 meter of sea level rise worldwide will cause a lot of trouble. The Dutch are ready for this. They faced that problem before. But if you just take a quick look around the world about what a 1 meter sea level rise would do, you realize we have a lot of infrastructures, harbors, airports, industries, residents that are within a meter of sea level rise. And it's going to cost billions of dollars for any city to adapt to that. So that's going to be a big change. And it's going to creep slowly. So the danger with policy is that they sit on this until things get really bad. And the longer we wait, the more damage it will do down the line. That's for the big glaciers in Antarctica and Greenland. The mountain glaciers also will contribute because they're melting like crazy. Now, the mountain glaciers will have another impact, which is freshwater resources. That's especially true in the Andes and the Himalayas. People rely on glacier melt to have a continuous supply of fresh water. So that's going to change into something that's dominated by precipitation. When it rains, you have water. When it doesn't rain, you have less. That's going to cause some problem to adapt to that. But I see it as something very important, but not as impactful as sea level rise.
We really need some proactive policy decisions being made. So do you have ideas or suggestions based on your work so far?
Well, in this time of crisis, I do like what all the other climate scientists are doing. I do my job as best as I could to inform the public mostly and policymakers. But don't forget, policymakers are elected by us. They will do what we elect them for. Don't expect them to save the world unless you voted for them to save the world. You cannot say, well, we should ban greenhouse gases tomorrow and use something else. Well, you're going to have to build that something else in the first place. It's going to take time, no matter how willing you are. It's going to take some time. I think what I would like to do in the coming 10 years is to work with my colleagues to sort of remove some of these uncertainties that we have about the system, get these critical observations that we need to make the models a little bit more reliable. We know the models are too conservative right now. That's what worries me. They give a projection to policymakers that's too small. It's going to be bigger than that. My point is not to scare people, is to get something which we feel we can look at this projection and say, yeah, we think this is in the ballpark of where we're going to be, at which point policymakers can make their decision. And another aspect of all of this is reducing our greenhouse gas emission and changing for clean energy, which is one of the most important acts we have to face. It's not a bad thing, and it's not a painful thing. It's something we have to do anyway. So let's do it sooner rather than later, and we're going to be better off. I am absolutely convinced that there's not going to be suffering along the lines. We're not going to be worse off down the line. We're going to be better off. It's a win-win situation. Let's do it sooner. What's really important for the public is to say, we want this now. We want you guys to start working on this now, not once we have death from climate change, for instance, right? You see the debate right now on wildfires. People pay more attention to wildfires because people die of wildfires in California. That was not the norm, having people die. So now it's unbearable. Sea level rise, we don't have death from sea level rise. But eventually we will, when people refuse to move, when people will have to immigrate to another country because they cannot live where they are, and there will be conflicts. There will be casualty. And then at that point, people will say, well, this is unbearable. We need to do something. The danger of that is that it's going to be a little bit late. It's probably in our genes. We react once we are facing a danger that could kill us. Then we say, wait a minute, okay? It's not a comfort zone here. I might die, so we're going to do something. And we're very creative when it comes to that. We're a very creative species. We have to be wise enough to tell ourselves, we don't want to get to that point. We're smart enough. We trust science enough to say, we don't want to see how bad it could be.
Yeah, I definitely don't want to see how bad it could be. As far back as 2014, you've been telling audiences and media that we're well beyond the point of saving certain glaciers.
Yeah.
Most of us, when we hear something like that, end up feeling a sense of inevitability and apathy about the situation, possibly even depression. Mm-hmm. And yet, here you are in 2023, still motivated, still studying glaciers and reporting on your findings, still speaking to the media. How do you keep doing this work if the future looks so bleak? Are there any points of hope that you keep going? That keep you going?
Oh, absolutely. I see hope. I see that the message is being heard. I see that there's a sort of grassroots reaction worldwide on people who say, you know what, we've heard enough about this to take action. We'll keep listening to the science, but we know enough to start building up clean energy, changing the way we manage the planet. I think especially among the young people, they go like, okay, we got it, Eric. It's time of trouble. What can we do? And if you tell them what to do, they'll do it. What is critical is to translate that grassroots movement into something that's embraced by a political system, right? We have to have elected officials who say, among all the priorities on my table, and boy, do I have a lot, because we have to take care of our people here. Climate change is one of the top, and I'm going to make sure that I will implement legislation, I will implement things in my local neighborhood to help, to make my contribution to the effort that's going to happen worldwide to make a change. And not only that, encourage people around me in my country, but also in other countries to do the same. And if they don't have the technology, well, share the darn technology with them to make it possible for them to do the same thing. This generation is quite generous in helping each other. So I'm speaking to them.
Mm-hmm. You've touched on this a bit already, but what's one concrete action you think listeners could do in their own lives, either as researchers or as citizens, to address the challenges surrounding glacier melt?
Everything we can do in our own lives, which goes in the right direction. We're not perfect. We're not going to do the perfect things. We're not perfect at recycling. We're not perfect at reducing our greenhouse gas emission. But every effort we make to be more conscious of the impact of what we do on the planet is an effort well spent. It will add up. I'm really convinced that it comes down to people around the world to take their own action, regardless of what they might hear in the media or hear from a politician, to say, you know what, I'm going to do it this way because for me it's important. Will count. For earth scientists, tell it as it is, right? Sometimes I hear my colleagues studying glaciers and I'm like, hey, you're missing the point. These changes are mind-boggling and you're trying to dismiss it. Tell them how serious this is. They need to know the scientific evidence is very solid. The ways to mitigate climate change are there. The technology to do that is there. We have all the tools. We don't have to invent or create nuclear fusion to get out of this hole. We have everything we need to get out of this hole, let's say in the next 10, 20, 30 years.
Well, that's a fantastic message of hope and action to end this episode of Down to Earth. Want to learn more about Dr. Eric Rignot and his work?
I'm working on the documentary with the French TV right now, so it's going to have a lot of stuff in it.
Be sure to follow and rate the Down to Earth podcast on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Irina Hansek of ETH Zurich and the German Aerospace Center for her support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.